Hi everyone, this is Alexis, and in this video we're going to look at 7.1 from Chapter 7. Chapter 7 is about the normal probability distribution. So we've talked a little bit in the past about our bell curve, our data that's normally distributed, and so that's what we're going to be looking at mostly in Chapter 7. In 7.1, we're going to briefly start with one other distribution before we get to the normal distribution. And as you'll recall, in Chapter 6, we did talk about some discrete probability distributions, but now here in Chapter 7, we're going to be looking at continuous probability distributions. These videos will go a little bit faster than our normal lectures went in class since we're not interacting as much. Just remember you can pause at any time and go back and re-listen to something. So for a continuous probability distribution, our random variable x can be any value, not just those nice integer numbers or nice whole numbers, but it can take on any value. So a probability density function is an equation used to compute probabilities of continuous random variables, and it must satisfy the following properties. So these are a little bit familiar. The total area under the graph of the equation over all possible values of the random variable must equal 1. So that's just kind of going to the idea that all the different probabilities that can happen have to add up to 1. So we talked about that in some of our previous chapters. The height of the graph of the equation must be greater than or equal to 0 for all possible values of the random variable. So that kind of matches up with our individual probabilities having to be greater than 0. We could never have negative probabilities. This uniform distribution is a continuous probability distribution where each value of x has the same p of x, the same probability. The graph of the uniform distribution will always be a rectangle, so it's kind of the boring one. It's before we get to this bell curve. It's just a rectangle. The range of the x-axis will be the lowest x value to the highest, and the height will be 1 over the range. So to calculate probabilities, we take the distance along the x-axis and multiply by the height of the rectangle. So here's a little sketch. Here is our random variable x. And here is, along our y-axis, our p of x. And so this starting point here is going to be the low x value. And this ending point here will be the high x value. So that's what they're talking about here in this first bullet. The range will be the lowest to the highest. And the height will be 1 over the range. So the height of this thing is 1 over range. And so basically you get this big rectangle. So what this rectangle represents is that for any individual x, you could pick any x along here along the bottom, its probability is going to be the same. It's going to be the height of this rectangle, which is 1 divided by the range. So the range is the high minus the low. And so probably you're wondering, why is this 1 over range? So if you think about the area of a rectangle, it is length times width, or base times height. Well, what we know here from number 1 up here is that the total area has to equal 1. So the area of this rectangle has to equal 1. So 1 is base times height. Well, the base we've called range. And then we could talk about the height. So then what is the height? You can solve this little equation for height, which is dividing both sides by range. So the height is 1 divided by the range. So when you have actual high and low x values for this, you'll be able to actually calculate what this 1 over range is in terms of a number. So here's an example. Suppose, this is a funny example. Suppose a friend is always late. She is late between 0 and 30 minutes, with all intervals between 0 and 30 being equally likely. Draw a graph of this uniform distribution. So we need to have our range on the bottom. So what we know is that x equals 0 is our low, and x equals 30 is our high. I think if we make each box be 5, that's reasonable. So 5, 10, 15, 20, 25, 30. So right here is 30. And so then we can figure out what our height needs to be. So our range is the high value minus the low value, which is 30. And then our height is 1 over the range, which is 1 over 30. Now that's the only value we're putting on the y-axis, so it really honestly doesn't matter where you put it. So I'm going to say, what was that, 4 boxes? Every 4 boxes is a 30th. This is pretty random. Don't stress too much about that scale. You just need something to get started for yourself here. So now this is our rectangle. That is our uniform distribution. So x and p of x. Now in part B, we're being asked to calculate a probability. What's the probability that your friend will be between 10 and 20 minutes late? So if we go back to that second bullet on page 1, it says to calculate probabilities, take the distance along the x-axis and multiply by the height of the rectangle. So I'm going to use some probability notation here. I'm looking for the probability that x is between 10 and 20. So that interprets as that she's 10 to 20 minutes late. I'll go ahead and use the equal signs. So that probability, according to the first page, is the distance along x multiplied by the height. So the distance along x from 10 to 20 is 20 minus 10. It's like a smaller little range. It's a subset of that whole range of 0 to 30. So 20 minus 10 is 10. And the height is that funny little 1/30th. So 10 times 1/30th is 10 30ths, or 1/3. Okay. If you want a visual for that, we can just go up to our picture in part A and say, well, from 10 to 20 minutes, I did each of these increments by 5. So there was 10 and there was 20. And so if I shade that in green to match with my green for part B, you'll see that that green is 1/3 of the whole probability distribution. Okay, here's another part. This is another probability question, but what is unknown is a different part. The wording of this one is a little funny. I think there's a homework one just like this. It's 10 o'clock. There's a 20% chance that your friend will arrive within the next how many minutes? So remember, she's always late, somewhere between 0 and 30 minutes, and it's equally likely, according to this question. So this time, let's start with the word probability here. So probability is distance along x multiplied by height. So this time, we actually know the probability. It's a 20% chance. So I'm going to write that as 0.20. The distance along x, I don't know. But this is the same probability distribution for this whole page, so I do know the height is still 1/30th. This is question mark times 1/30th. So this is actually a little equation we can solve. We can multiply both sides by 30 or divide both sides by 1/30th. So 0.2, our probability, times 30 is 6. So 6 is the distance along x. So that refers to 6 minutes. So it will be in the next 6 minutes. And if we go back to our picture in part A, if each section along the bottom was 5, then 6 is right around here. And so if you shade that part in, that should be 20%. 20% is also 1/5. So the red part should now be 1/5 of our total. Okay, so that is actually all we're going to do with the uniform distribution. It's really kind of boring. It's just that rectangle. Not a ton of data, follows that pattern, but enough that we want to just talk about that with that one example. So what we're going to get most of the time for the rest of this chapter and some of the chapters moving forward is we're going to be working with the normal distribution. So our symmetric, bell-shaped curve, it has one mode, that highest bar in the middle, and it has a mean mu and standard deviation, sigma. Okay, so our mean is right there in the middle, or of course sometimes we talk about the mean, if we just have a sample, as being x bar. So we have our empirical rule. We saw this earlier. This still holds true because we are looking at a normal distribution. So we have 68% of the data within one standard deviation above and below the mean, 95% of the data from 2 standard deviations above the mean to 2 standard deviations below the mean. And if we go out 3 standard deviations on both sides of the mean, we get 99.7% of the data. So almost all of the data falls in here. There's just tiny, tiny, tiny little bits out here. We also have our z-score formula, which we did see before in the past. So z tells you the number of standard deviations you are above or below the mean. If z is positive, then you're above the mean. If z is negative, then you're below the mean. And this was for a population, this formula. For a sample, we have z equals x minus x bar over s. And so we might not have thought of this a lot in the past when we worked with z, but basically what we're doing when we calculate a z-score is we're turning our individual data, our x values, into z's, so that now the mean is 0 and the standard deviation is 1. So we're kind of simplifying our data and scaling it all to the same standard. Now for the normal density curve, the probability curve, the curve is symmetric about the mean. The mean, median, and mode are equal and are located in the center of the distribution. The curve has a single peak, and the peak occurs at the mean mu. So we've seen the bell curve before, but now we're thinking of it as a probability distribution. The normal curve has inflection points, and this is kind of a fancy math concept. So if any of you took pre-calc or calculus, or you're ever going to take it, this is actually a calculus terminology, but an inflection point is where it changes from concave up to concave down. So it has 2 inflection points at mu plus or minus the standard deviation. And this is just for your information. You're not going to be tested on that. But the total area under the curve is 1. So everything over here is 0.5. Everything over here is 0.5. And as we probably talked about, but it's been a while, these tails that come on the left and the right, we definitely talked about tails because we talked about skewed left and skewed right. This one's not skewed left or skewed right. It's normal. It's equal and even on both sides. These tails technically go out forever. They never actually get down to 0. They never actually touch the x-axis. But most of our data falls in those 3 standard deviations, 99.7% of our data. So we don't worry too much. We just know that there's a little bit out there further. And that's about it for 7.1.